So I welcome all the participants for the afternoon session. Afternoon session will be conducted by National Infotech Surat. National Infotech Surat is associated with us from last 5 years, and we have established MOU with National Infotech Surat, and we are doing lot of work in coordination with, and they are guiding us very well as far as the different projects and the trainings are concerned. So I also welcome National Infotech Surat for this STTP. National Infotech Surat is actually working in the field of power electronics, embedded system development, and custom industrial automation. National Infotech has been established in the year of 2001. Initially started with as a training center in the embedded system, power electronics, industrial automation, and later NITech diverted for developing educational trainers for the academic institutes and industrial solutions. So I welcome National Infotech Surat, and I hand over the charge to Mohammad Junaid for the further process.
Yes. Thank you, sir. Thank you, Thakre sir, for introducing us. So I'll again briefly introduce ourselves on where we are excelling ourselves, and then we will have a session from Mullah sir, and we will see also see I'll brief you that what we are going to see in this next 2 hours, and also uh, in this week. Okay, so let me first present my screen. My screen is visible, right?
Yes, yes.
Okay. So first of all, I will welcome everyone to NITech. So we are majorly three field working in this area. So we are the RAM electromech, then power tech marketing, and us, the national infotech. So I'll brief you the little about our these two partner companies. So first of all, I'd like you to introduce to RAM electromech. So it is working in the field of providing electrical solutions and automation, and also the power quality solutions. He's having the vast experience and quality and eligibility to provide the electrical solution. And so moving on to the power tech marketing, the power tech marketing, the main area of the power tech marketing is the manufacturing voltage stabilizer and UPS, and also isolation transformer, and also the IPFC panels. And then moving on to us, this is us. We, as you all are aware about that, we have the MOU with the SSBT Jalgaon since the last 5 years, and we are also excel in the making of the manufacturing of the educational trainers, and we also provide this training courses and the industrial solution, which we also provide to whomsoever is seeking the industrial solution. So moving on to today's topic. So in this week we are going to see the power converter development process. So in this 5 days, what we are going to learn through these 5 days, I am briefing right now that we will be seeing this many topics. The first is STM32F407 VG controller with Weijung, and then exploring the GPIO in the microcontroller, and how to interface with LCD, the ADC and DAC, then development of single phase inverter and three phase inverter development. So this the this microcontroller peripherals, we are going to see what peripherals are used in order to develop the power electronic converter circuits. So apart from this STTP, we also happen to have this many courses aligned with us that if someone wants to do in their project about Arduino programming, they want to learn. So they can also learn from us that we have a small 1 week or 2 week program for each of this specialization, and we also provide the project support. And I help the students in wherever they are facing any obstacles. So these are the few courses we are offering. So whoever seeking this want to learn some FPGA programming, they can learn from us. And if they want to learn in the MATLAB simulation or PSIM simulation, the TMS, the Texas Instrument DSP controller, STM, which we are going to see through this 1 week, and also in electrical module and our industrial automation. Okay. So with that, I will introduce you to our today's speaker, Dr. Muhammad Ashraf Mullah. So he is currently an associate professor in Department of Electrical Engineering, SVNIT Surat. He is also a member of IEEE and many other societies with more than 23 years of teaching experience. His mentoring activities of NITech for developing power electronics and microcontroller based systems. His research interests include solar and wind energy conversion, electrical drives, power quality, and active power filters. And he has also published more than 50 articles in national and international journals and conferences. So with that, I will hand over this session to Mullah sir. Over to you, sir.
Thank you, Junaid.
Yes. I'll stop.
Good afternoon. Am I audible? ORG?
Sir, you are audible.
Okay. Okay. So I thank the organizer to give this opportunity to National Infotech and me also. So tomorrow also one lecture is given to me. So participants, you must have gone through the schedule of the program. Research and development are two important pillars of our electrical engineering discipline. And we may have many ideas, but unless we can verify that in the laboratory, uh, we will not be able to provide such solution to outside society. So under that scenario, afternoon session is fully planned where development related aspects you will be exposed to. So morning you will have some good lectures, some concepts, some research problems, some society problem solution through power electronics. But in the afternoon, how to do that thing in the laboratory, that is what is planned. So I can say that it is a very good schedule what the organizers have prepared, and I'm sure uh, this talk the overall 5 days talk should give you understanding of both research as well as development aspects of the theme of the STTP. Now coming down to today's approach, so there are many platforms for implementation of circuits in the laboratory. Even some experts were saying that the population of digital controller is 7 times more than that of human population. So on each human, if we average uniformly, then 7 controllers are working. So it is a big community. So one such platform, ARM Cortex controller, we have selected. And today, so controller means it will be some electronics, so number of transistors, some peripherals are there. And it is not analog chip where it will give some functionality to the input. You will have to program it. So the additional part will be you will have to learn how to program this. Now majority of our learning is happening in MATLAB environment. So the idea of this afternoon session is how to migrate your MATLAB Simulink concept to the digital controller. So how to program the controller utilizing MATLAB Simulink environment, that will be the theme. So there are several ways we can program. We can write some assembly language code, C language code, some cross compilers, some tools provided by chip manufacturer. Okay, but here for these 5 days, we will try to verify some concept in MATLAB and how to migrate that solution to the microcontroller. That way we will try to program. Okay. So today's agenda is I will try to introduce you what is in general power electronic system and what is the features of this microcontroller, what we have selected, why we have selected this microcontroller, what are the ways to program it. Okay. Now since we need MATLAB, that drag group approach of dragging some wire from here and there and not adjusting some simulation parameter and running the simulation, getting some waveform will not work out. So the second part, what we need, so what way we should prepare our MATLAB simulation so that that model can be migrated to this digital controller. So actual circuit will work with your logic. So second half or second 1 hour is diverted towards what way MATLAB programming should be done. So my PhD scholar Rajan will talk about how you should prepare your simulation in MATLAB so that that MATLAB model can be dumped to this microcontroller. Okay, so this is the agenda. I hope it is okay.
Yes, sir. Yes, sir.
Prasanji, how to interact
Yes,
with
sir. Yes, sir.
participants? They will speak in between or?
No, they will be asking questions in the last only.
So in the last they will ask questions. So they will just
Yes,
listen
yes.
and at the end they will ask the question. Okay.
Yes.
Okay. You please keep giving me feedback in a case I am not audible.
Yes, sir. Yes.
Okay. Anytime it happens, I am just speaking, but it is not reaching other end. So outline of the presentation, motivation of project-based learning, power electronic systems, what basic power converters we have, what are the important building blocks of power electronic system, what microcontroller peripherals we need for power electronics, and then details of this STM32F407 microcontroller, and what we expect uh, at the end of 5th day. Some points are mentioned here. Okay. So at Surat SVNIT, since long we have understood that experiment-based learning teaches more than any other media. So any animated thing, other thing, but the experiment teaches you more than any other media. So we keep experimenting. So In 2008, one STTP we attempted where 8051 board is given to different participants and some driver power circuit through which power electronics basic four converters, rectifier, inverter, AC voltage controller were constructed. And since then, we are pursuing this. So we keep organizing number of STTPs in our syllabus, student syllabus also number of experiment instead of that ready-made box where only terminal thing we can see. So how starting from programming to a complete circuit arrangement in open form, all the many experiment we adjusted. Present version is we have four courses what we are running, where one is on power converter, another is on electrical drives, third is on renewable energy, and fourth is on power quality. So instead of only talk-based discussion, over here we will simulate something, we will prepare some small model and we will verify the concept. So that way these courses are taught. So we keep organizing such courses. Okay. So those who are teachers or maybe pursuing, they may keep interacting. So SVNIT all activity on this Facebook page, my students are managing. And as Junaid told you, a specific tool if you want to learn, maybe FPGA programming or C programming of this controller or PC based programming of TMS controller, then at NITech they keep organizing such courses. It will be a short course of 1 week, maximum up to 2 weeks, and you will start doing something related to maybe suppose PCB designing is there or something like that. So these are the two pages. If you are interested, you may subscribe to that so that you will keep receiving the updated information over there. Now coming down to today's theme. So basically what is there in power electronics? So it is to convert or process the flow of power by supplying voltage and current which is optimally suitable for the load performance. So we may be having electrical power available in a form which is not optimally suitable for the load. So older time induction motor was a constant speed motor because only 50 hertz, 60 hertz alternating voltage current were available. So we could make this motor to a variable frequency motor by changing the stator frequency. So that has been obtained via some power converter where we can generate any frequency. So two possibilities, we may be having input available as a DC supply or AC supply, and both of them we should be able to convert where variable voltage, variable frequency output you can generate. Okay. So this is what is the definition given in our Mid-Mohan sir MOOC. Now, in order to do this, what all element we need? So three important parts are AC/DC supply and load that will remain. In between, you will be having a semiconductor switches. So some arrangement of semiconductor switch, which can convert AC to DC, DC to DC. So those four combinations we should be able to perform. Okay. Now semiconductor switches will be controlled via some control signal, which will be normally generated by some digital controller. So in order to get the reference output voltage, some duty ratio or firing angle of power semiconductor switches will be adjusted by digital controller. Okay. Many times it is a closed loop arrangement where field information we will measure and that will also be given as a feedback to a controller. So it will try to force a reference value near about the actual value. Okay. So this is typical power electronic system. You can imagine anything. It can be a motor drive or it can be a renewable energy system. Every place it will be like this. Okay. So if you go 20 years back, this all were not possible. So four important factors which has contributed to this is power semiconductor switches. So we have new types of semiconductor switches coming up, which has made this field. Now switches alone cannot do anything. You require a very high speed digital controller. So we have DSP, VLSI, microprocessor, microcontroller, SC, where at megahertz of suppose this microcontroller, it is working at 168 megahertz. So hundreds of megahertz those chips are running, and in a nanosecond or picosecond we can make the computation. Another good thing which has happened in electrical engineering is new control algorithms we have invented. So fuzzy logic, artificial intelligence, our PI controller, PR controller, many things has contributed towards this development. And finally, there was a demand. So prior to this, very inefficiently electricity we were utilizing. So there was a scarcity of electricity, and we were utilizing very inefficiently. Like if we take nowadays we have a BLDC fan. Previously or now also we'll be having a older fan at our house which is utilizing a single phase induction motor. So if you try to read the data, then it is around 75 watts single phase induction motor. But presently, whatever BLDC fan is available, if you try to compare the rating of that motor, it is around 25 watt BLDC motor, which is giving us the same mechanical output. So what I am trying to highlight is extra 50 watts we were just making because of using that inefficient single phase induction motor, which we have overcome by utilizing this brushless DC motor. Okay, so the amount of power in which one fan was fed with a single phase induction motor, it is possible to have three such fan fed with the same magnitude electrical energy if it is this new brushless DC motor fan. Any comment? So if we explore the main heart, power semiconductor switch. So there are three categories. Uncontrolled switch. So the switch will become on and off by power circuit signal. So across anode and cathode, some voltage is coming, it is forward bias, it is conducting current. So diode and diac are the example. Then semi-control switch. So our thyristor, very widely used, where we can trigger the thyristor. So we can delay the conduction of thyristor by gate pulse, but once it will become on, nothing we can do from gate side. So only the power signal, whenever there will be a negative cycle of your supply, then only it will become off. So in that context, Nedmohan sir classified this as a semi-control switch. And the third category of switch are fully controlled switches, which can become on and off from the control circuit itself. It seems somebody's mic is on. If not required, please mute it. So if you try to take a recent picture, what is happening in semiconductor switches. So this is one slide I copied from Infineon.com, one of the leading semiconductor manufacturer. So if you see this picture, there is no alternative to thyristor if it is hundreds of megawatts or gigawatts of power. So thyristor and diodes are the only switches in very high power range. Okay. At very high frequency, we have MOSFET and IGBT is intermediate. So up to medium voltage range, we have IGBTs available. So up to medium voltage 3.3 kV, commercially IGBTs are available. Okay. So insulated gate bipolar transistor. So all these three, thyristor, IGBT, MOSFET, we constructed utilizing silicon material. Now field is saturated and no other possibility of rearranging those semiconductor layers to get high voltage, high current and high frequency simultaneously was possible. So present time they have started exploring new types of semiconductor material, that is silicon carbide. SiC stands for silicon carbide, and then gallium nitride. So GaN based material. So where high frequency, high power switches they are inventing. Okay. So at this stage, SiC diode and MOSFETs are available, and few GaN devices are also available. So new types of semiconductor switches are coming, and the roll of switch is exactly same what our switchboard switch is doing. So when we will make it on, it should allow full load current, and when we will make it off, it should break the current, and full supply voltage will appear across switch terminals. So same role we will expect from all these semiconductor switches. Now energy density and power density are further concerns. So when we utilize this power converter in some application, let me say vehicle application, aerospace application. So apart from technicality, the size will also matter. So as a result, we need to operate these devices at very high frequency. Then size of energy storage element, that is inductor and capacitor, can go down. Second, thermal remain a major concern. So if we require to mount semiconductor switch in large aluminum plate, and then it will also increase the weight and size of the equipment. So the heat generated by your device should also reduce. So silicon carbide, this is silicon carbide based 10 kilowatt 3-level multi-level inverter, and if you read the dimension, the size is lesser than our laptop size. So it can process 10 kilowatts of power. It can convert DC to AC up to 10 kilowatt, and the size will go like this. So power density is more. In a lesser volume, we are able to process a higher magnitude power. Okay. So from this website, I copied this. They are the manufacturer. So this red board is a microcontroller generating gate pulses, and the verticals are all semiconductor switches. Some backside energy storage elements are seen, and that is how DC will be converted into alternating. Okay. So additional point is people would like to have a higher power density. So in a smaller volume, you should be able to process. Now going back to the basics. So what are the different types of power converters? So in our power electronics textbook, 4 circuits: AC to AC, AC to DC, DC to DC, and DC to AC. Okay. Now the scenario will be completely different if you try to explore all this in laboratory. So if you start learning these circuits in the laboratory, then your understanding will be there are only 2 circuits where we have a DC supply as an input. So in textbook it is chopper and inverter circuits. So when DC supply is an input, just generate some random gate pulses and make semiconductor switch on and off, and that is how DC to DC or DC to AC conversion will be possible. Okay. So this is one category of circuit where input will be DC and microcontroller role is very easy. Some gate pulses microcontroller should provide, which will make the required conversion. Now yes, you can interrupt me and speak in between also if required. Can I continue?
Yes, sir.
Okay.
Sir, please continue.
Okay. So another category of circuit is having AC supply input. So now we cannot randomly give some gate pulses to this circuit, because whenever there is a positive cycle, particular semiconductor switch should be controlled. Whenever there is a negative cycle, then particular semiconductor circuit should be controlled. So as a result, we will have to detect where the supply positive, negative cycle is starting in the power circuit, and that input we will have to give to the microcontroller. Then microcontroller will generate once again some gate pulses which can be connected to that circuit. Then it will be able to trigger those semiconductor switches. Okay. So here practical classification is circuit working with DC supply, circuit working with AC supply. You don't require any feedback if DC supply is there. You require supply feedback if it is alternating voltage. Okay. So normally I ask my student which circuit should be taught first, and everybody will say rectifier because it is a long chapter of 100 page in the textbook, and every time we teach that. But if I say you construct half wave rectifier and show it to me, that is difficult. Then if we say that buck converter you prepare and show me, because just some random some frequency pulses can make your buck converter. Now laboratory thing, so in theory we teach them different semiconductor switch arrangement where AC can be converted to DC, DC can be converted to AC. So only power circuit we teach them. Now when we work in the laboratory, we require three things. Number one is logic circuit. So this is the brain part. Which semiconductors which switch should be on and off at what instant of time, that is decided by logic circuit. So signal processing circuit which will generate logic control signal. Okay. So low power arrangement, there is no major power involved here. Nowadays microcontroller work with not even 5 volt, it is 3.3 volt VCC. So some 3.3 volt one chip where logical pulses it is generating. Now the second part, normally what we neglect. So can that pulse trigger the semiconductor switch? So answer is no. There are many issues. Wiring issues will be there. Driving issues will be there. So we require in between something called as a driver circuit, which is once again a low power electronic circuit, which amplify control signal to the level and form what we require to drive. Okay. So for example, our thyristor require gate current. So pot pin cannot provide gate current. We will have to convert that voltage signal into gate current signal. Our MOSFETs require maybe plus 15 volt to remain in on state. So our controller cannot provide that plus 15 volt. So we'll have to amplify the signal to a level and form what the power semiconductor switch will require. So this stage will fit in between logic circuit and actual power circuit. Now power circuit, what we learn in theory, same can be extended there. So bridge arrangement converts AC to DC. Okay. Then edge bridge arrangement can convert a 4-quadrant chopper, something like that. Okay. So power circuit will be made up of some combination of AC/DC sources, load, and power semiconductor switches. Giving an example, so here we are taking one AC supply through diodes, we are rectifying it, and we are producing this DC voltage. Okay. One leg of semiconductor switches are shown here. Okay. So here some output we are converting. So if it is DC to AC converter, this VD voltage will be converted into AC here. If it is DC to DC converter, then this DC voltage VD can be converted as DC voltage also with the same arrangement. Okay. So this flow, AC source, diode, electrolyte capacitor, and IGBTs, that is our power circuit. So if it is a 10 kilowatt arrangement, 10 kilowatt power will come from AC source and it will go to load via this path. Now in between we need remaining two blocks. So first is logic circuit. So some low power microcontroller which is generating where T plus and T minus should be on and off. Okay. Now the gate pulse will be connected between base and emitter terminal of this transistor. So in between you require electrical isolation. So just like transformer, you should have a different ground. Then only that signal you can connect between gate and emitter, So electrical isolation we need to provide in between. In order to provide electrical isolation, you require one separate power supply. So we should have auxiliary power supply. So if you have 10 numbers of IGBT, 10 numbers of auxiliary power supplies you will need, so that isolated gate pulses can be provided to those semiconductor switches. Okay. So in terms of previous slide definition, the power circuit is one where a huge magnitude power will flow. Logic circuit will decide when gate pulse will be on and off, and driver circuit. So it will amplify this logic level to a level what semiconductor switch will need. For example, practical IGBTs, we normally provide plus 16 volt to keep the IGBT in on state and minus 8 volt to keep the IGBT in off state. So here the output of this circuit will be plus 16 minus 8, but when it will be plus 16, it is decided by logic circuit. So this way, these three blocks, logic circuit, driver circuit and power circuit will constitute your overall power electronic system. So normally we take optical isolator, so photodiode, phototransistor. So this side, this is isolated part. So this side ground will be different. Now in order to have a different ground there, you require power supply. So lower side, if you check, it is Zener regulator. So we can construct one power supply. So suppose my objective is to give plus 16 and minus 8. So I will generate 24 volt DC here. Then two Zener diode, one is of 16 volt and another is of 8 volt will be connected here. And I will say that this is my common point. So wrongly we use the word ground, but I can say this is my common point. Then with respect to this point, the upper potential will be 16 volt and lower potential will be minus 8 volt. So we need to make the gate terminal to fluctuate between plus 16 and minus 8. So whatever 0, 1 will come from this logic circuit, we will trigger these two transistors where upper transistor will connect plus 16 volt here and lower transistor will connect minus 8 volt here, and midpoint is directly connected with source terminal. So that is how, with respect to source terminal, the gate terminal potential will be either plus 16 or minus 8. Okay. When it will happen, it is decided by logic circuit. So this is one typical driver circuit for MOSFETs. I hope it is okay. So 3 unit will make your power electronic system: logic circuit, driver circuit and power circuit. And this is one example where we can correlate the role of power circuit, role of driver circuit and role of logic circuit. In theory, we learn only power circuit. In laboratory, we require all three of them, and then only you can constitute this. So as initial slide I said, we attempted that let us learn this project base. So we developed these few cards. So we have some thyristor cards, we have some IGBTs cards, okay. Then we have some microcontroller card which may be 8051 basic 8-bit controller to this ARM controller to some FPGA controller, okay. So whatever numbers of semiconductor switch you have, so this is one power card we constructed where 6 IGBTs are there. For each IGBT there are power supply of plus 16 minus 8 volt, previous circuit whatever I explained. And here microcontroller will say which IGBT I require, when it should be on, and the actual pulse which will go between gate and emitter terminal of IGBT will be plus 16 minus 8, not 0 to 3.3 volt what microcontroller will generate. Okay. So this is the real picture of this card. Inside a driver IC for first card, TLP250 IC is used, and for the second card, an Infineon driver IC 1ED020I12 that is used. So the small transformers are 6 SMPS transformers, and plus 16 minus 8, 6 identical supplies are constructed, and this rectangular chip is that Infineon driver IC. So here a logic circuit input we will connect, and here 6 pulses we will get. So here the level of signal will be 0 to 3.3 volt, And here the net output what you will receive is plus 16 and minus 8. All of them are independent and electrically isolated. So your IGBT may be at some high potential in the power circuit. Directly this gate pulse you can interface with the power circuit. Okay. So this is the driver card example. So some high power arrangement where we have a rectifier, we have an inverter. Okay. Then we require some sensors. So output current, suppose it is a PV application, then DC link voltage current you want to sense. So some sensors are mounted inside and the same driver card is connected here. So we can connect sensor output to our microcontroller. Then we can process some logic and whatever get pulse we will generate that we can interface here. So this is IGBT modules are inside, diode rectifier is inside. So that way this unit also we constructed. These are the picture of sensor card. So this is a whole sensor current, a whole current sensor. So it can measure AC/DC current. So actual current, your full load current, maybe per 25 ampere current will be scaled to a 3 volt, what can be connected to the microcontroller. Similarly, this lower blue color sensor is a whole voltage sensor. So this is 700 volt voltage sensor where 700 volt AC/DC can be scaled down to a 3 volt, what you can interface with the microcontroller. This is a thyristor card. So this is pulse transformer to drive the thyristor, because here we require gate current, not voltage signal. Okay. This is 3-phase thyristor driving card. So we have 3 phases, each phase giving positive cycle, negative cycle, some gate pulses we need to connect. And these are those 6 independent switches. So if it is thyristor, I can construct single phase rectifier, I can construct AC voltage controller, any arrangement I can construct utilizing this power card. Okay, so this is the picture of power card where it is not rigidly connected in bridge configuration. Okay, you can form any connection. You can have a AC voltage controller, single phase rectifier, 3-phase rectifier, any arrangement you can construct. These are the microcontroller kit. Okay, this is the CAM controller kit around which you will be demonstrated all functionality. Okay, so now further I will speak about major on digital controller, because that is the brain part. So how to convert DC to AC, AC to AC, how to write that program, that I will try to elaborate further. But I would like to ask at this instant, if you have any question related to whatever I presented, I encourage you to ask.
अनम्यूट कर मेरा. हाँ.
कैसे कराएंगे और इस पे क्या
No question.
If you have, you can ask.
I can go further.
We'll see.
Last only. Okay. So now a slightly different topic. So as a power electronics engineer, normally there remains a fear of digital controller, how to learn all this, because any controller, if you take 1000+ page data sheet will be there. Okay. And it always create a distance. So if we try to summarize based on our today's discussion, what all we need. So we have to control some semiconductor switches. So some gate pulses we have to generate. What is gate pulses in digital world? So digital world will have only two status, 0 and 1. That is 0 volt and VCC. So if we can toggle some pot pin with our desired rate, then that job is done. So if we learn to write a small program where I require 10 kilohertz pulse with 50% duty ratio, then that part is completed. Okay. We have a group of circuit which works with AC supply. Then some input will come. So our zero crossing of supply will be given at the interrupt pin, and starting from that point we will have to generate the delay. So another requirement will be some digital input we should be able to accept. Okay, we should be able to work with interrupts, and then some timer which will generate the 30-degree delay or 90-degree delay, whatever we require, that we should be able to produce. Okay. So these are two essential parts for controlling semiconductor switch. Then comes field information. So field information will be analog values. So some voltage you are sensing, some current you are sensing, which may be AC or DC. So this value we should be able to take inside the microcontroller. So now slightly difficult thing will be there. So first we require sensor. Sensor will give us some voltage. Now it is a digital controller, so it can understand only digital thing. So we need to convert this analog value to some digital value, and then we will have to interpret it. Then it will become the actual sensing element value will be available inside your program. And the third part what you will need is a complex algorithm. So your logic, what way after receiving the feedback you will process and you will generate gate pulses. So that also you should be able to write. So here I have tried to summarize what all we are looking. So in terms of controller, they say GPO, general purpose output. So some digital output we should be able to generate. In order to do this timely, we require timers. Okay. Our major power electronic system is this 6 IGBT arrangement, 2-level inverter. So over there is a special requirement like upper and lower pulse should be complemented. There should be some date time between upper and lower switch, otherwise it will create gate short circuit over a DC link. So we can have an advanced timer which can support this. Okay. Some motor drive application where some Hall sensors or encoders we want to connect, then we require general purpose input. Once again, you require timer to measure the frequency of those pulses, to convert those pulses into the actual RPM or position of the motor. Okay. In a industrial application, we connect encoders for precise control. Then QEI stand for quadrature encoder interface. So that peripheral we require. Then we require analog to digital converter. So number of analog values like our 3-phase system, 3 voltage, 3 current, we should be able to take inside. Then the system present position you will be able to judge. So a 12-bit ADC with 3.3 volt are available on whatever microcontroller I will be showing you. There is another useful peripherals what you should whenever you select a digital controller you should see that is DAC. So whenever we are constructing or we are writing logic in Simulink, what we do, we apply a scope at different sub intervals and we verify which place that computation is not happening properly. So with a real signal how to debug if something is not happening. So there is a digital to analog converter. So inside any quantity you are calculating inside, that can be taken out utilizing DAC on oscilloscope. So just like scope in the MATLAB, on oscilloscope you will be able to see your calculation. So you have made some calculation of voltage and current, whether that product of power is happening properly or not. So if you have a simulated output available, with real signal also you can take out that power, calculated power on the screen, and then you can verify whether it is happening properly or not. So DAC is also another useful peripheral. Then we require some keyboard and LCD to start stop the system, to display the system information, and to protect against abnormality we require some external interrupts. Okay, so these are the minimum peripherals for power electronics application you should read on selected digital controller. If it is available, then your life will be easy. So as I commented, this is a big community. It is very difficult to say which microcontroller is good. And whenever we heard the word CPU, normally computer comes in our mind, but computer, laptop, tablet, mobile, it is only 30%. 70% is this industrial controller. Okay, and population is 7 processor per human being. Okay, so there are many standardized things happening in that world also. Okay, so like 8051 is known to all of us. So 8051 is a core developed by Intel, but since beginning Intel diverted themselves into computer processors. But the good thing what they did is they provided license of this 8051 core. So in that context, today also 8051 based microcontrollers are available from different. So likewise, whatever controller we have selected, it is ARM controller, it is also generic cores. So ARM is a company which provides only core like Intel. So different semiconductor manufacturer will license ARM core from this company, and then they will construct some chip for some end application. So maybe motor drive is a target, then different peripheral they will provide on their chip. If renewable is a target, then different peripheral they will provide. If your metering is a target, then different peripheral they will try to provide on the chip. So that way different microcontroller they will construct. Okay. One big area where big players like Texas Instrument, Microchip, Atmel, so they have their own core also. So peak series controller only manufactured by Microchip. TMS 320, 28335, very popular in academics, but only constructed by Texas Instrument. You will have to use their tool chain, their core only for this controller. So there are two ways to classify: generic core and proprietary core. AVR we know. Okay, this Arduino and other controller very popular, but it is only by Atmel, and only Atmel can supply that controller. No other. Whereas the first category is generic. From Texas Instrument also you can find ARM controller. Okay, reverse case is not possible. Okay. So since it is a big community, present end is towards 32-bit controller, and ARM controller are most popular in industrial application. People would like to use 8-bit and other. They say same cost, 32-bit controller is available. Why to use 8-bit controller? So that way they are promoting. So now the feature of the controller around which you will learn all this. So it is 168 megahertz controller. Its maximum, sorry. Sorry. Okay. So its maximum throughput is 210 MIPS, million instruction per second. So 1 million is 10 lakh. So this will convert to 21 crore in our calculation. So million instruction per second. So this can execute as high as 21 crore instruction in 1 second time period. So it is quite fast. Okay, almost instantaneous. Any computation you can perform. All DSP instruction it can support. So like we include mat.h and then sign function we utilize. So all such things can be possible with this series of microcontrollers. Memory is one big area of microcontroller. So this controller is having 1 megabytes of flash memory, where number of time number of time we can write our program. So we will do some alteration in MATLAB, and then immediately through USB cable our microcontroller kit is connected, and the same program will be dumped in the flash memory of microcontroller, and new performance of your converter you will be able to see. We require a large number of pins. So this controller is having a large number of IO pins. The microcontroller works with 3.3 volt here. But the good thing is they have constructed the controller in such a way that giving 5 volt to each pin, it will not get damaged. Now this is not possible in any other controller. So by mistake, higher than 3.3 volt given to TMS controller, it will damage the chip. So that is unique thing what ST Microelectronics has provided. Very rich in form of a timers. So there are 17 timers. 3 of them are utilized for system purpose. Still we have a total 14 timers available for general purpose use, where 12 16-bit timers and 2 32-bit timers we can utilize. Then ADC, analog to digital converter. So it is a separate hardware placed on that chip itself. So there are 3 numbers of ADC. There are 3 numbers of ADC this controller is providing. Now each ADC can be multiplexed up to 8 channels. So if you have analog hungry application, then 8 into 3, total 24 channels, up to 24 port pin you can utilize for taking analog. Okay, and speed is also very high, 2.4 MSPS. Once again, M is million, so million is 10 lakh. So 24 lakh, then SPS is sample per second. So we can take 24 lakh sample per second with this ADC, and it is a 12-bit ADC. So your analog value will be resolved into 12-bit number. So there are 12 bits where value can be 0 or 1. So 2 raised to 12, that many numbers you can construct. So all values 0, then last value 1, then 1 0 1 1. So likewise, a total 2 raised to 12 numbers, different numbers, it can process. 2 numbers of DAC, once again 12 bit is available. Rarely you will find a controller providing DAC. Okay, then DMA is available. Communication is one big area. So some other chip you want to communicate. So SPI, I2C, or serial communication, everything is supported. Advanced connectivity, that is USB, Ethernet, that is also supported here. And then for electronics application, audio, video, camera interface, that is also supported here. Okay. So for power electronics application, lower 5 points are okay. Normally we will not be exploring. DMA we will utilize to reduce the processing speed of the controller. So now next, so these are the features. If you download STM32F407 datasheet, on the very first page, it is around 1700, 1800 page datasheet, but very first page, all these things are mentioned. Now programming, so 2 ways. One is C language, not even C++, only C language, embedded C language. So ST is providing this software, STM-Cube, where whatever peripheral you require in a visual form, you can configure it. So suppose I am taking 3 voltage, 3 current, so I will configure 6 numbers of ADC, and at what rate that current voltage I want to take inside the system, that I will configure from here in visual form. Then comes, I will have to generate 6 pulses for my inverter. So what frequency pulses I want to generate, that also I will configure for that. And the output of this STM-Cube is one C project, where main file will be open, and after getting your inputs, how you want to process. So that logic only you have to write in C language. So that way development will be very easy. So this is one method of programming this controller. A second method is this. So if I'll show this block diagram to some MATLAB expert, they say it is a MATLAB simulation, but this is not MATLAB simulation. This is a program for controlling the grid synchronized inverter connected with solar panel. So here 100-volt DC link you want to maintain. So actual voltage through ADC. So there is a ADC block here. So actual voltage we will sense through ADC. It will be compared with 100, some PI controller. Okay. Then some transformation we are performing. So I'll be having IDIQ values. So if I am not processing reactive power, then IQ reference is 0. Then IDIQ 2 more PI controller, and then some assigned PWM or space vector generating gate pulses. Okay. So through Simulink environment, utilizing this Wisum block set also, you can program this. So end output of this is a number of ADCs it will read, it will process this logic, and it will generate the gate pulses. Okay. So we will demonstrate all this, but in general at this stage you can say these are the two methods. If you are comfortable in C language, you can go for approach 1. If you have a fear and you are very much comfortable in MATLAB Simulink environment, as next session you learn how to prepare this simulation, and then through MATLAB Simulink only you can program this controller. So in summary, I will end here. So in summary, in this presentation, I have tried to show you the on-chip peripherals of this controller, what you will be utilizing for next 5 days. What are the important building blocks of power electronic system? I have just generalized. You can take any application. It can be motor drive or complex railway application anywhere. You will be having that system. What is the way of programming this? That I say. And I hope that this will help you to start working around this controller. Okay. So I will pause here. If you have any questions related to what I spoke, you may raise.
क्या लेना पता नहीं
So the presentation is concerned. If you have any queries, you can ask. I request all the participants. If you have any queries, you can ask.
Sir, can you enlighten about the price range of this STM32 with compare with the other type of controllers?
Can you, what is there in your mind when you say other type of controller?
Sir, little bit I have explored with the D space. Okay.
D space. Okay. That word is sufficient. Okay.
And
so D space.
But mostly, but what I observed, mostly this D space kind of controllers are very expensive, and mostly it is available in the what we call the research laboratory, we can say. Suppose if I want to work the individual research, so is it possible with the STM32 to buy this one with a lesser cost?
Yes, the cost is no way comparable with this space. So older time, if you go 5 years back, this space was the only solution if you want to do something with Simulink environment.
Yes, sir.
Okay, it is a costly arrangement. Minimum 5 lakhs plus. Even lowest version also, if you take 5 lakhs plus, yes, only one terminal, one student can work at a time.
Yes, sir.
And if you have arranged some circuit where some input output is connected with this space output terminal box, no other can use it. Okay. Even as an output, if you have generated some good output, how to give that output to some actual user outside, because this space output cannot be migrated to some microcontroller. Okay. So older time, the only motivation of investing this high cost was something doing from MATLAB. But now MATLAB itself has come up with some toolbox called embedded coder, where many microcontroller it supports. If you see the cost of this chip, it is in the range of $5 to $10. Okay. And the real kit what we will get, so ST will give some discovery card, it is in the range of 3,000 rupees. And whatever complete microcontroller kit this National INFOTECH is providing, it is in the range of 20,000 rupees. Okay, so where all source code and other thing are developing, so cost is no way comparable, and these are the plus
No,
minus. So whatever you
actually, I'm
whatever
having this basis three board of Xilinx. So just I want
Xilinx is
to.
also good.
Yes, sir.
If you have Xilinx board, then you explore SDIL coder in MATLAB. So there is a similar toolbox in MATLAB. Then some MATLAB blocks and some SDIL coder block working together, you can migrate your model to Xilinx.
Sir, but sir, if I want to compare this STM that you have explained with the Xilinx boards, then which one having the least
So you see,
complexity?
Xilinx is FPGA. It is a parallel processing. It is a parallel processing. Now this is a round robin. So you will be having suppose whatever logic you are writing in sequence, those instructions will be executed. So both are different. One case you have only logic gates. Okay. Now Xilinx you will not find any peripherals. So suppose ADC you want, so separate ADC chip you will have to take and you will have to interface with. It is only logic gates. Okay. So these are some plus minus, but in terms of speed, FPGA controller due to its parallel processing will be very fast even as compared to this 168 megahertz microcontroller. But you will not get any peripherals. So you will have to take separate ADC, separate DAC, then interface with FPGA, your Xilinx controller. That way you can construct the system.
Sir, mostly what happened now, we are very much we can say it is easy to develop the models in the MATLAB, being an electrical engineer, and most of the time we struggle with the what we call the hardware implementation using these kind of low cost controllers.
Right. So this is a small effort to show that, because I am also having a similar feeling what you are expressing. So suppose MATLAB if you take, do you think we know complete MATLAB? We know very little bit MATLAB, but comfortably we can go there, we can do something. So this digital controller also you consider as a tool. I have tried to highlight in today's presentation what is my requirement. I will have to generate some gate pulses. I will have to gather system information inside the system, and then I will have to write some logic. So if we start doing this, then in detail we can explore that as a subject. But as a tool, if we explore, then that difficulty will not come. So this microcontroller, FPGA controller, they are quite cheap as compared to Opel RT or DSpace. They are quite costly affairs, and as I said, only one student will work at a time, so not justified. And all money will go to foreign companies. Our traders will earn something small money. So that way, as a country, it is not good practice. But everywhere it is happening like that. It is beyond our control. Same thing you will be able to do with all these controllers.
Right, sir.
Okay. I hope it is okay.
Yes, sir. In between your presentation, I will ask many questions.
Any other question?
No, sir. No, sir. Right now it is okay, sir.
Okay. So we will interact further tomorrow. Okay. So I will pause here, and next MATLAB part, what way MATLAB simulation you should construct, that you explore. That is very important for further sessions. Thank you.
Thank you, Mullah sir.
Thank you.
I think we will move on to the today's second session. Shall we move on, Prashant sir?
Yes, yes, yes.
Okay. So we have with us Mr. Rajan Wamja. He is currently looking towards his PhD at Department of Electrical Engineering, SVNIT Surat. He has completed MTech from SVNIT and BTech from LD Engineering College, Ahmedabad. He is actively associated with the NITech for developing power electronics and microcontroller based system. His research interests includes solar energy conversion, electrical drives, and power quality. So he will be guiding us to the uh, importance of the discrete time simulation in MATLAB, and also he will brief us about the STM32 controller. Already, sir has also explained it, and he will also give some little bit of more details about it. So I'll hand over the session to Mr. Rajan Mamja. Over to you, sir.
Okay. Thank you, Junaid, for
Thank you.
this nice introduction. So I'm also thankful to the committee also for providing me opportunity to speak here and share my experience related to my work and whatever we are doing. That actually as an experience we want to share here. We will not here to share something new and something researchy work, but whatever we are doing here and that how it is useful to construct something, some actual hardware in your workplace, that we will take away from this all the experimental session. So for that, one important thing is, so how to accurately simulate a system in a MATLAB. That is a really important thing. Am I audible, Junaid, or can anyone give input? Am I audible?
Yes, sir. Yes, you are audible.
Okay, so I request that if anyone actually in this session, I required that you should speak and you should give some comment whenever I want. Yeah, Paresh sir.
Mr. Rajan, please start your screen. Can you start your screen?
Actually, I will share. Okay, I will share. Sir. Okay.
You just share
Actually,
it
there
and
is no
start.
presentation. I will demonstrate live, sir. There will not be any
Okay.
demonstration.
Okay.
Okay.
ठीक है.
Okay.
Okay.
Now, is my screen visible to everyone? Is my screen visible to everyone?
Yes, sir. Yes, yes, sir. Yeah. Please.
So in this session, the important thing is that generally we are doing a simulation, and whatever part in the simulation is there, generally we are not knowing that this we are doing also. So generally I want to share my experience to do the simulation here. So for that, whatever things or minimum things required to know related to simulation, generally all have done one or another way some circuit, power electronic circuit, they have simulated with MATLAB Simulink. So minimum basics I think you are having, but some advanced level, that what thing you should take care during the simulation, that will increase your efficiency or accuracy of doing a simulation. That is a major task. Then that points pinpointly I will highlight here. And other things is that this simulation will have many parts generally that we are not looking for. So out of that one part, we will directly take to make a program of that. That also we will see in this session. So first in this session, I want to clear that whatever simulation I am showing, that simulation is we have targeted to charge some 48-volt battery. So to charge that 48-volt battery, if we are having some 100-volt DC source or some AC source, from that we will make some DC. So we are having some DC of 100-volt. Using that, some 48-volt battery we want to charge. So which converter is required? Can anyone say that which converter is required? Which power electronics converter is required? We are having a some 100-volt DC, and out of that 48-volt battery we want to charge. You can unmute your mic and you can speak in between. Actually, this session will be interactive throughout the end. Okay, till the end it will be interactive. So please unmute your mic and you can speak. Hello. Am I connected? Okay, buck converter. Some okay, some is giving it. You can speak also. It is better that you speak and you can comment also. So buck converter is required. So generally to construct buck converter from the Simulink by library, we will take this component like some DC source of 100-volt I have taken. I kept some 100-volt here. Is it visible? 100-volt. Okay. So after that, some switch, diode, inductor, Then some battery I have not taken right now in this simulation, but I want that some buck output is there. So just my target is right now to verify the converter topology. So I kept some equivalent load of some 24 volts, so 2 ampere current it can draw if I hold here 48 volt. So this is the setup. So generally, if someone is there, it will do simulation like this. So is this clear? This simulation. So we required some power GUI. This all things we required, and some control system is required where we can give some gate pulse to this. So in actual circuit, we required some driver card to give this gate pulse, but in the simulation, we can give directly 1 or 0. Directly we can give 1 or 0 to this switch to make it turn on and turn off. Is this circuit is clear? Is there any mistake in this circuit? Can anyone say? So
No, I
correct.
think. Yes, correct.
What is the problem? Can you say?
Feedback diode is there. Is
It is there, sir. This is the diode.
there.
Okay, it is there. So first source, then switch, then diode. Here inductor at output side and output side capacitor and some load we have connected. So I think what converter circuit is very correct. So then input voltage measurement, input current measurement. To observe this, some scope I kept. To observe the inductor voltage, I kept some voltage I have taken and I am seeing in the scope. Then current measurement. This whole thing we have done. So generally, this is our practice. We do like this. Generally, we do like this. Okay. So now this is the first part. Now second part is this. Some PWM pulse we want to generate. So what we will do, we will take some constant. We will take some triangular wave in one or another way we will make. So I wish that this PWM frequency of this switch should be 10 kilohertz. So I made one repetitive sequence I have taken. Generally, it is our practice that we will take some triangular generation. And we are comparing it with some, so its value is oscillating between 0 to 100. So if I give 50 here, some 50% pulse or PWM pulse, it will generate here. So what is the thing we are doing is we are taking one triangular, and we are comparing with this DC value. So we are comparing it with this DC value. So that DC value will be compared, and whenever this DC is higher than this triangular, some pulse will be there. Means positive 1 will be there at output, and when it is lower than the triangular value, it is like similar to the comparator. So this is the comparator in a simulation. So it is name is a relational operator. So we will take like this. So now this is the some initial simulation I kept. So now I will highlight that what mistakes we are doing during the simulation, and our output is not coming correct, and even we are not knowing that our output is not correct. So our all the parts are clear. So first thing I want to highlight here. So to at any circuit, you should have minimum two things. One is a correct knowledge of the theory. So now the related to buck converter, I think most of the participants are very much clear. So first thing we should know the theory accurately. So according to theory, this should happen. Okay. And second thing is that how can we accurately simulate this thing? So if output is not coming, so there will be two reasons. One, we don't know theory, or we kept something wrongly, or we have misconceptualized something. So that is the one reason that your output will not come according to desire. Second thing is you have very good at theory, you have very good basics of whatever you are doing. You don't know how to simulate it correctly. The word you know simulate, but how to simulate it correctly, then also your answer will not match with whatever concept you are having. So here I want to highlight some parts that generally we are doing. So here you can see these are the some required block I have taken. So for time being I am removing it. Here if you want to observe some AC quantity, we will generally utilize the scope. So whenever I want some to observe some DC quantity, generally I will use this display. So to observe that what is happening in the converter. So these are the this is the one simulation. So now is there any mistake in this simulation? Can anyone say mistake or this is correct? Correct. Is there? time being, if it is correct, you should say, okay, sir, it is correct. It's look like correct. Now we will see if something will happen. Okay. So can anyone say, is it correct or any doubt you are getting here? So, is this block inserted properly? Or doubt you are having? Unless you will not give some input, I will not go forward. This is actually my style here. At least one input from any participants. Am I connected, Junaid?
Yes, sir. Yes, sir.
Right.
You
Am
are
I
connected.
connected?
Yes,
Okay,
sir.
thank you. So, but participants are not responding. So, okay. So ground is required. Someone is saying is ground is required, but my answer is ground is not required. Without that also it is perfect. If things if you have in mind, you can speak by unmuting it, or you can put a comment. It is visible to me also. Input from the participants. So can I consider that this is the perfect circuit? There is no issue or any other things required from your side. Now it's your turn to give input. Then I will speak again. No response means okay, it is correct. Now this is I am feeling good that you gave some response that sir, you did very well work. It is looking accurate. So 100 volt we have taken, and if I keep here 50%, so I keep 50. So this is I am entering in the percentage. So this triangular is having a value magnitude. PWM constant is too high. Someone is commenting that PWM constant is too high. I didn't get. Please unmute your mic and you speak. I think you can speak, sir. Is it possible that they can speak? Or
Yes, sir. Yes, yes.
okay, they are not speaking, just commenting. So I thought that okay, my mic is not okay. Okay,
They
not
can
an
speak.
issue.
They can speak, sir.
Thank you,
Okay.
sir. So here actually, I think this is the perfect. So you can see the repetitive sequence. So this is increasing from 0 to 100 and it will have a frequency of 10 kilohertz. I said like this. So I am sure that there is no problem here. I am finding it will come here. There some constant we will compare. Some PWM pulse will be generated of 50%. That will go to the gate driver here to the switch and it will switch at 50% duty cycle. Switch at 50% duty cycle, and if this voltage is 100, then what should be the output? Can anyone comment on it? Output क्या आएगा ये register के across में? What will be the output across this register? Can anyone say? If I run it, output क्या होना चाहिए? What is the output in this? Input is there. Input. If I run this for a 1 second, okay. So what will be the output at this side? According, this is the buck converter. Is 50%. Yes, Jitendra ji, आप कुछ बोल रहे हैं? Oh, 50. So some DM Gaikwad ji is saying that it will be 50. So if I run it, it's 50. So okay, this is very nice. It is working correctly. So there is no issue. We can say that it is working correctly. Okay. So that Gaikwad ji also right, and someone also commented. I actually missed that comment. So that is 50. Now if I do 60, what will be the output? Can anyone say? मैं इसको 60 करूँगा तो output क्या आएगा? Now goal to speak or comment. Anyone can speak. Even coordinator also can give their input also. So,
60 volt.
60. Thank you. So now if I run it, you can see it is not coming 60. Not coming 60. Circuit is correct. Comparison also correct. We have seen that at 50 it is giving correct output, but at 60 it is not giving correct. Let us check for 40. I will not now say that you say for 40 also it will come. It should come 40 according to buck converter theory. But it is coming some 20. Why it is happening? No very well theory. That's why you was giving the answer that sir, At 50%, it should come 50. At 40%, it should come 40. At 60%, it should come 60. Here, output is coming something different. There is a mistake. Now, anyone say some few word for this? कि कहाँ पे हम गलती कर रहे हैं? गलती कर
Sir,
रहे हैं.
maybe in the inductance and capacitance, we have taken pure inductance and capacitance. Maybe we have the some resistance in series inductance and the parallel capacitance at the output side.
So one, okay, sir. Thank you for your input. One, Kishore ji is saying that there might be some issue of that whatever capacitor and inductor we are taking, there might be some issue. But my answer is there, issue is not there. Any other input? Okay. Any other input? Any input you want to say? Because I think one, whatever participants are there, they have some experience with this MATLAB environment. Maybe if you are not having also, then they can see. But who are having the experience, they can share their experience. That sir, here might be the problem. Is there any input? I continue with there is some issue. So how can we solve this issue? But it is looking like very nice. So what I found is when I was working initially, similar problem I was facing. I was very good at concept, but when I put in the simulation, it was not working here. Now after I follow the one thing that always I will try to make a simulation in a digital manner. So now what is a digital manner or sorry, discrete manner? So there is three word. There are three word. One is a digital. One is analog, and one is discrete. Can anyone say that what mean by digital, what mean by analog, and what mean by discrete? Input at least you should give. What mean by digital, what mean by analog, and what mean by discrete? आप discrete मतलब क्या समझते हो? Analog मतलब क्या समझते हो? Just give your input in one or two word. Answer. Answer. Okay, say sir, we don't know. You just carry forward. You explain. Then it is okay. Any comment? No, yes, something. Okay. Analog is a continuous time. Okay. Thank you. Thank you. Some inputs are there. So if we see the digital means whatever pulse it is getting here. To turn on the key, get switch, we want generally digital pulse. So generally digital controller will generate this pulses in terms of 0 and 1. Digital circuit are generally giving output in terms of 0 and 1. That generally it will be in level, so 0 or 5. If you take a controller, or if you take some other controller, it will be have 2 level only. Yeah, either 0 or 1. So 1 in terms of some voltage. So then when we come to the analog circuit, it will have an infinite resolution. Infinite resolution means it is pure in the form of analog. So here if small part you will take, small part also will not have any part. If you make further small part, if you zoom it, there will not be any discontinuity. It will be always continuous. So analog means like this. Now what is a discrete? Discrete means we are sampling this signal. We are sampling this signal at some rate like this. It is in analog in nature. It is alternating in nature. I can say alternating in nature. But it will have a lesser resolution. So the resolution is controlled by the sample time. So this signal is called the discrete signal. Is called as a discrete signal. So any controller processing any signal are always in the discrete manner. So कोई भी कंट्रोलर आप प्रोग्राम करोगे वो पूरा डिस्क्रीट ही है, पूरा डिस्क्रीट ही है. डिस्क्रीट है, अगर वो कंट्रोलर डिस्क्रीट है, हमें प्रोग्राम भी उसमें डिस्क्रीट करना है. सो व्हाई कैंट वी गो फॉर डिस्क्रीट सिमुलेशन? So whatever simulation I have done in analog manner. So if you do analog manner, so what mean by analog manner? So you can see here in the power GUI, we have used configuration continuous. Continuous means it is like analog. So first thing we did is you take analog. Now here I want to show something. If I open this display in time, give me 1 second. So here in sample time you can see here all. If I click, you can come to know something here. So you see this part, is this part visible to you? Is this part? It is. I went in the display. In the display I went in sample time. So if we all we do, then it will show that which part is sampled at which rate. So you can see this is the continuous. The black part, whatever you are seeing, that is continuous. Here some FIM is that final fix in minor steps, something like this. Here this part is an issue. I will show it to you. Okay. And some this color will be some infinite. That is that also I will explain. So all the sampling time of this circuit is not in our hand. So we have not set even that which circuit should sample at what rate. सबसे पहले की बात है कि इस सिमुलेशन में कितनी सर्किट है, किन किन सी टाइप की सर्किट है वो भी जानना जरूरी है. So if you take this simulation, so there are two types of circuit. One is a control circuit. And one is a power circuit. This is the power circuit. Now can anyone say what is the difference between power circuit and control circuit? Can you say what is the difference between power circuit and control circuit?
The power circuit mostly deals with the higher voltage level and higher current level, while this control circuit will deal with the lower voltage level.
Thank you. So whatever control logic we will write, control logic will be our control circuit. It will not be nowhere related to this power circuit. So you cannot even connect this block with this, because these two blocks, this blocks and this block, these power blocks are different. So you can see here the two circuits are there, or two types of blocks are there, we can say. One is corresponding to some signal level circuit, and one is corresponding to the some power level circuit. So this source is a power level circuit, this meter is a power level circuit, this IGBT is power level circuit. But here what repetitive sequence we are taking, this repetitive sequence, that is not a power level circuit, this is signal circuit. So these are the signal circuit generally we are utilizing for a control system. So this same circuit we will use for programming a controller. So first thing we should know that how can we discretize this simulation? How can we control the sampling time of each and everything? Because our digital controller works in the sample manner. Even in the displays also we will face this problem of limited sampling capability of displays or controller. So that we will see later if time permit. But here we will strict that how can we solve this problem? हमारा ये पूरा जो आ रहा है वहां पे प्रॉब्लम कहाँ पे है? So if I run again and if I observe this, if I observe in this scope, you can see something is there, some problem is there here. Okay, so you see, so one repetitive sequence, it is compared with DC value. So our first input is DC value, whatever we are giving. Second input is the scope is our repetitive sequence, and third is our pulse generated. So you can observe here, repetitive sequence is not correctly generated. That's why our pulse are not correctly generated, and that's why our buck converter is not working correctly. But until unless if I have not done this all sample time, I could not even know that problem is here. नहीं चलता यहाँ पे problem है. Are you able to find that problem कहाँ पे है? Is it clear? Problem हमें मिल गया कहाँ है? Find the solution. Connected.
Yes, sir. Yes, you are connected.
Okay, some error came here that, but are you clear? Here is a problem. Generation is having a problem. अब हमें problem मिल गया तो उसका solution क्या है वो find करते हैं. तो generally आपका concept सही होता है, आपने सब block सही रखे होते हैं, but generally the sampling time of this each block is decided by your MATLAB Simulink. Our task is that how can we control the sampling of each block. Each block means power circuit block and control circuit block by our own. उससे हम इस सिमुलेशन को एक्यूरेट कैसे बना सकते हैं. So is this clear, this part where we have some problem? Where we have some problem. Now I will show you another simulation. Okay, another simulation of a same. There we will see. This is another simulation where I made necessary changes. Now you see the previous part and this part. So the same circuit with some nice GUI or nice presentation with a nice presentation there where I have arranged this circuit very nicely. So generally first mistake students are doing that they are putting anywhere the scope. In your simulation, if you want accurate result and observability, clear observability कि कहाँ पे प्रॉब्लम है वो हम कैसे पता करेंगे, how can we know? तो पहले आपका जो ब्लॉक्स आपने रखे वो एक्यूरेट रखने चाहिए, उसमें कुछ मीनिंगफुल प्लेसमेंट होना चाहिए. There should be some meaningful placement of the block. So here I am using some go to and from that is not equal to the wireless transmission. So we are wirelessly transmitting some current measurement and we are using somewhere. So same circuit I have taken, same 100 volt, same things I have taken. Now if I see in the simulation, if I want, here V in is there, this is V in, that will be 100. So I am measuring V in and I am observing here. Three part, one is a power circuit, control circuit, and one is the observation. You can see, this is the observation. Okay. So now if I run it with 50%, so and then you can observe that here output will be 50 accurate. You can say this is very accurate output at 50, and then you can again say that sir output you was getting with that circuit also at 50%. Now you check with some other duty cycle. Please check with some other duty cycle. Otherwise, how can we know? So let me check it with some 60%. If I run it, you can see exactly 60 output I am getting. 60. So now my concept is clear and my simulation is exactly matching with whatever concept I am having. So how it has happened? By knowledge of discrete simulation. Just by knowledge of a discrete simulation. Can I make this simulation discrete and how can I control the sampling time of this simulation which give you the greater accuracy in the simulation? So it will exactly match with your concept. But you should be clear with the sampling time fundamentals and the discrete simulation. Now can we go for discrete simulation to know that what is a discrete simulation? Now side some input. Is this now simulation looking accurate or not? Is there any problem? Is there any problem?
Yes.
Input from
Yes, sir.
participants.
Yes, sir.
Okay.
Yes, sir. Yes, sir. Sir, any problem,
Okay,
sir?
thank you. No, I
Okay.
thought that I am disconnected and I'm asking
No,
no
no.
is replying.
You are already
Okay.
connected. Okay.
Thank you. So here you can see I have divided this circuit in the three part. One is a power circuit, control circuit, and observation. So if I do any simulation, I will have these things. These things. So now what is the discrete simulation? Still I didn't spoke. So now I will come to that point. So now before that, I want some input from the participants particularly. So what is this GUI block and why it is required? Generally students ask this thing. So what is this GUI block and why it is required? If I remove this GUI block, what will happen? Input from the participants. One question that why this GUI block is required. This is the GUI book, power GUI block. Why it is required in the simulation? If I'm not putting it, what will happen?
There will be an error.
Yes, someone is speaking.
There will be an simulation error.
I'm actually not. You are not audible. Actually, some problem is there.
there will be a simulation error if you don't put that power GUI
There
block.
will be the simulation error. You are saying that. Okay. So you are right. But this power GUI block is controlling, it's controlling the sampling time or the functioning of this power component that I want to convey here. This power component, it is controlling. So if in your circuit, this power component is not there, if these power components are not there, then this power GUI is not required. So let me give you demonstration. So if I if I if I disable these all things, power circuit component control shift X, and this control shift X. So this I have disabled now. Run this, if I run this, there will not be any error. You can see there will not be any error. So to simulate, so there will be two part. One is a power circuit, as I have mentioned earlier, and one is a control circuit. Now I came to know that if I take if I take if I take this block now, if I enable this source, just source I am enabling, and if I run it without power GUI, now you are seeing the condition without power GUI, some power component I am trying to simulate. You see, so it is giving error. It is giving error. You see, it is giving error. So from this exercise, we can conclude that this power GUI block is required for a power circuit component, not for the control circuit parameter. So this is the first takeaway from this lecture. So this is controlling all the sampling of this power circuit. So let me enable this circuit again. Shift X is a shortcut for this control shift X. Okay. So if anyone is not knowing, okay. So now I will take you to some configuration. Now first thing I want to say here, the control circuit I have discussed. So there are two parts. One is a control circuit, one is a power circuit. I'm taking two variables. One variable is a control circuit time. When you start the simulation to make it discrete, five changes you should make. First change is you should take your solver option. In your solver option, you should take this as a fixed step, and this will be same for all the laboratory session. In the laboratory session, after this, you will come to know that we'll make some program of a controller and we will dump in the controller. So for that also same configuration will be there. Okay, so this is the fixed step. Here in the solver, in the solver, in the solver, in the solver discrete you should select. After that, that is a second change. This is first change, this is second change, and third change is you should give some time here. So I have taken one variable, its name I have taken as a TS control CKT. So it is some meaningful name I have given. Sampling time for a control circuit. Control circuit sampling time will be controlled with this. So whatever value I give, if I give 1 microsecond, it will sample all the control circuit part as a 1 microsecond. The third part you should take care. Fourth part is here. Here in the tasking, there might be some tasking. So you should keep it single tasking. So our controller are generally single tasking. So we are making simulation in the discrete and with single tasking. At a time it will do one task like this. So this four change actually I told five, but these four changes are required here. So this value TS control CKT, that is a control circuit sampling time. Whatever time I will put in this variable, that variable value it will take in the sample that I will show you now. Okay. So now when I put this TS circuit, so this was the setup for setting the our control circuit. Now if I go further deeper, so now here in the power GUI, now this is the fifth change which is required generally. So fourth change we have done for control circuit. Now we will come to the power circuit. So in the power circuit, just give me a moment. Okay, this block is coming somewhere. Okay, so in the power circuit, here you should make it discrete. You can choose any solver here in the power circuit. For power circuit, you can take bicodular or testing. Both are giving the accurate answer. Okay. Then here I wrote again the same similar syntax, TS power underscore CKT. It's mean that it is a sampling time for power circuit. So as I already proved that this block is for power circuit. So we will control the power circuit sampling using this. Okay. So now these two variable I have taken. Now I will go inside that simulation. So now again I'm clicking here at this point. I'm clicking here. I'm clicking here. From that I will go to the model property. I will go to the model property. In the model property, I will go to the callback. You remember this. In the callbacks, I will go to the initial function. I am setting some time here. So this is the fundamental sample time I am setting, that is a 1 microsecond. So generally people are choosing 10 microsecond, 5 microsecond. So that is also one reason that you will not get accurate result. So lesser sampling time will give the lesser accuracy. So time being I am taking 1 microsecond. There is also some fundamental that how you can select this fundamental sample time. So this is the TS I am selecting, that is a 1 microsecond. So to make this simulation accurate, okay. So now second variable I am taking this TS power circuit. So this TS power circuit I am selecting as a 1 microsecond. Here you can see that is 1 microsecond only. This is also 1 microsecond because it is same as a TS. Then control circuit also I am selecting as a 1 microsecond. But I am saying that you should give the 1 microsecond. It might be difference. So this voltmeter sampling and this relational operator sampling can be different. So this is controlled by power GUI and this is controlled by your model configuration. So in model configuration you can control sampling of this block, and power circuit sampling you can control using this block. Okay. So now here some TS outer loop I have taken, that I will come to it later. So here second thing is TS switching. So switching frequency I am selecting is a 5 kilohertz here. So T switch I use one variable, that is a T switch. So if 1 by 5 kilohertz, that is nothing but 200 microsecond. So now if I come back to the our triangular, so you can see, so I am taking now some 5 kilohertz switching frequency. So we can take 10 kilohertz also, not an issue. We can take, I have taken 5 kilohertz switching frequency, 0 to 10, same triangular I have generated, but with a 5 kilohertz sampling. So now here some comparator get pulse, and get pulse will come here. Then some input output. So these are the some change I have made. And if I again go for display, sample time and all at on annotation, so you can come to know that some color code it will come. So this color code you can see. So now you can see. So this power circuit component are in the red color. Power circuit components are in red color. So that red color is having a 1 microsecond sampling that we are controlling. As I told earlier, we are controlling the power circuit component, and that is through the power GUI. Then you will come to know some other color. So this scope is having some different color. So what I am doing is I am sampling the data in the scope as a lesser rate. That is a 10 microsecond. 10 microsecond. So you can see this is the 10 microsecond. Why I am doing that? That because to save the processing. जनरली एक कोई साइन है ऐसा, उसको आप 1 माइक्रोसेकंड से सैंपल करो या 10 माइक्रोसेकंड से सैंपल करो, विजिबिलिटी विल बी सेम, विजिबिलिटी विल बी सेम. तो टू मेक योर सिमुलेशन फास्टर, आपको क्या करना है, स्कोप को डेटा को कुछ कम रेट से सैंपल करना है, जिससे आपका सिमुलेशन फास्ट बनेगा. एक्यूरेसी तो यहाँ पे मिलेगी, एक्यूरेसी तो कंट्रोल सिस्टम इम्प्लीमेंटेशन नहीं मिलेगी, बट आपका सिमुलेशन जनरली किसी का ऐसा होता है, if you are complaining that our simulation are working very slow in our computer, but that might be that you are running your simulation for 5 seconds and storing all data in the scope. That's why your simulation will be slower. So we can control the rate of the scope also using the same fundamentals. Okay. Then you can see some blue color. This is very important. So can anyone say that what is the rate, sampling rate of this blue in microsecond? Can anyone comment on this? Blue color का sample time क्या है? Using this value, can you calculate it in the microsecond? In microsecond, what is the sampling time? What is the sampling time of this constant? It is a blue color. You can comment always. You can comment. Any comment? Or you can speak also. Okay, you are seeing there is a change in the color. So I am sampling it at lesser rate. Why I am sampling it at lesser rate? Can anyone give answer? Can anyone give any answer? So this is very useful for programming of the controller. This aspect is very useful. That's why I am stretching here. So we are sampling this at a 400 microsecond. Why? Anyone say why I am taking 400 microsecond only, not on any other? So sampling time of this is a 400 microsecond. Why? Input, comment. Okay. So there is no response means something is missing from my side. Am I properly delivering this? ADC will be at same rate. Some answer is right. But now someone, okay, fast response. Thank you. Fast response. But there is some misconception here. You see. So triangular we are generating. Now, as I mentioned earlier, if we take this triangular, so time frequency of this triangular is 5 kilohertz. 5 kilohertz. It is equivalent to the time. 200 microsecond. 200 microsecond. So now you see, if I am taking one reference wave, just you focus here. Okay. So I am taking one more triangular here. I am taking just two cases. So now this 40 is a reference wave. So now let me take a blue color. Blue color is not here. Okay, this color. So first thing I am doing is I am taking one signal like this. I'm taking one signal like this. One signal I took like this. Okay. And one signal I am taking like this. One more signal that I am taking like this. This is the comparator value. So what is different between these two signals? Can anyone comment on this? Can anyone comment on this? Can anyone comment on this? So this is 200 microsecond. This is 200 microsecond time period of this triangular. Both are the same. But reference value is sampled at different rate. So whatever this 40 volt we are sampling, that 40, not 40, that reference value, that is sampled at every 200 microsecond. You can see. So this value will be same for at least 200 microsecond. So this is called the discrete control. So if you change this 40 value too quick like this, too quick. So there is no comparison. You can see it can compare here only. So your triangular and reference value can compare here only at one time only. So your pulse width will change at one time in one triangular cycle. There will not be any other change. You can see here one change you will get, here you will one change. So if you are getting one change over a one triangular period or one switching period, then why unnecessary to sample this 40? Why unnecessary to sample this 40? This 40 is a reference wave at higher rate. So if the switching frequency of the signal is 5 kilohertz, then 200 microsecond will be the period. So we can give. So this is to save the processing energy of your controller. So if you sample it higher rate, your processing power it will take higher, and it will if you want to construct large system, you cannot construct. So selection of sampling time in your control is a very important task. So in simulation also we are following same, and this same control we will implement in the controller also. So I'm running out of time, so we will see. I need more 10 minutes, I think. So can I take more 5 minutes or 10 minutes, sir? Prasant sir, Paresh sir, can I take more 5 minutes?
Yes. You can conclude in 5 minutes.
Hello. Okay. Okay, so maximum 5 to 7 minutes I need. Okay, only 5 to 7
Fine,
minutes.
sir. Fine,
So
fine.
what I mean to say this, okay. So what I mean to say is, so this part we will program using STM32 controller. This part, whatever observability you want, so we want that our output voltage and output current, this all should be visible. So this, for this visibility, we will program our LCD, where we can see the V output, V input. Right now, any constant current or constant voltage operation is happening for charging. That we can observe in this. So this part, if you accurately simulate, the same part can be useful for the programming also. As sir has shown some grid connected inverter control. So it is a similar part. So we will copy this control part and we will program it using the proper interface that you will see in the next exercises or next laboratory session. So with this, I want to say that, so this was some open loop control. This was some open loop control, but in the discrete control where we are controlling the power circuit and control circuit time, where your reference signal should be sampled at the less than or equal to the time period of the signal or switching frequency. That save the your processing power, that you will come to know when you implement it, or when in the upcoming sessions you will come to know, you will get more clarity over this. This is the technique where you can do the discrete simulation, where you should control the timing of the power circuit and you should control the uh, uh, timing of this control circuit and power circuit both. Now I will show you some closed loop control, where I will control the same circuit. I will control the same circuit. So this is the same circuit, same parameter. But here change is that I will give some change in input voltage that I will demonstrate. So with the change in some input voltage, there should not be any change in output voltage. So there should not be any change in output voltage. The same control circuit. If I put this switch at lower side, it will run in open loop. If I put in upper side, it will run in closed loop. So this is our control circuit. Same control circuit I can use for battery charging. So you will be surprised that before 3 days we required that some constant current charger. We need some constant current charger. So in 1 day we have constructed that constant current charger to charge a battery available in our UPS, our laboratory UPS. So it was deep discharge. To make it charge, we required some constant current charger. In 1 day we have constructed it. So I will show it last also. So same control I have implemented there. I have copy pasted this control in a controller and I have implemented it. It was working very fine. So here just constant voltage I am showing. So you can see here, this is the input voltage which I will vary in the buck converter input. Here output voltage you can see, that is a controlled output voltage. So what I am taking, this is the reference voltage I required, that is 48 volt battery I want to charge in constant voltage. So some reference voltage I am taking from output to boost converter, then some PI controller. It will give me some duty cycle. With the duty cycle I will run the switch and it will maintain constant 48 at output voltage. So now if I show you here, so you just focus here. You focus at two places, one here and second here. This is output voltage, that is a control using this, and third here. So first you observe here, second you observe here, third you observe here. So now what will happen if I run it? When I run it, now you see simulation. So here something is not visible. So you see 48% duty cycle is there, 400 volt input to maintain 48. So now if input is changed to 80, this duty cycle should be increased because input voltage is reduced. So it action happen automatically. When this voltage is increased, at that time duty cycle is reduced. So our V in is increasing, our duty cycle is decreasing. So this automatically will maintain, this control system maintain the output voltage to 48 volt by regulating the duty cycle of the switch. So irrespective of the change in input, so we are not observing the input. So this is some small control system I am showing in the simulation, which is working very correctly. So we have given some change in input voltage. then also our battery or our output of the converter is hold at 48 volt. So if you want that, I can run again, and we will go for some practical aspects where we have implemented that in real time. So 48 is maintained constant. So now here it will become 80. You can see here it will become 80. It will become 80. So then duty cycle is increased, and again it will maintain to 48. So it is maintained to 48. So again it increased to 120, duty cycle is reduced, it maintained to 48. So this control system is working perfectly. Now the same control system we can copy paste in the coding of STM32, and we can make constant voltage charger in our laboratory, or in your laboratory also you can make. So here some slide I want to show here. So this is the same controller where you will see the different operation. Here in this controller, so whatever analog input we need to sense, so you can see, so here this DC link this voltage we need to sense, this output voltage, because we want to maintain this output voltage to constant, or we can sense the current also. So here our ADC will be very useful, that we will program, and that ADC value will give here, whatever from the sensor, whatever ADC we want, that something we want to sense, we will give here. So I have given voltage here and current here, voltage here, current here. Okay, so as a input. Okay, then some reference value we should give. So that reference value I have provided using this port. Here some potentiometer are there in our controller. So this is the one part of our controller, and this is the upper part of controller. So here some LCD is there. This is the STM controller. This is the STM controller. This is the STM controller. You can see this is the STM controller, and here our lower board, which sir was explaining. So in the LCD I am observing the input voltage. This is, you can observe, similar to simulation. It is very easy to program the controller. So this is the actual voltage, this is reference voltage, this is actual current, and this is reference current. I have given reference 2.2, and it is running in the constant current operation. So this all the information we can program very easily using this environment. So you can see the full. So if I give the 0.2 here, so if I change this reference, it will change this also. So we can program LCD. Here some keys are there. So I am using this key to turn on the system and turn off the system. So I have the right that I can control the operation. I can control the operation. Here I can say. So if I want to turn off, if I want to turn off the pulse, I can turn off the pulse by keep pressing. Or if I want that it should work in the open loop and closed loop, also I can control in the programming environment. So same thing we have done in this program, where this key we have used to turn on and turn off of the circuit. This key we have used to turn on and turn off. This key we have used to change constant current to constant voltage. So it can operate in constant current and constant voltage both mode. So if I press this key, it will go from constant current to constant voltage. So similar programming you can do, and in the upcoming session, it will be demonstrated during the laboratory, that how can you program this controller, how can you program this LCD, how can you program this key, or how can you program this ADC, and some small tasks you can do very easily using this controller. And if you have some fear for programming, that can be easily overcome using this MATLAB Simulink based environment. So whatever logic you are constructing here in the discrete simulation, same logic we will use to program the controller. So that was a main lecture, that how to do the discrete simulation. So you should control. Okay. So now I am closing it with this. So I hope this is clear to everyone, that you should do the discrete simulation. Any comment? Any comment?
If you have any queries, you can ask. All the participants are requested to ask the query.
Any query you can ask. This is the way we are doing the discrete simulation. So here we are controlling the all the time, power circuit time, observation time, as well as the control circuit time. So you can always observe that this part we are keeping slower. This part we are keeping always slower than the whatever switching frequency, F switching, because of higher accuracy as well as the processing, saving of the processing power. Thank you, Avjit ji. Okay. So if
It
you
is
are
wonderful,
not
session, sir. It is very wonderful session.
okay, thank you, thank you. So I think you can take something from this lecture, and this will be very useful. So any doubt, any other doubt related to this? So you try to simulate your whatever simulation you are doing in the discrete manner. So that is my suggestion. So it will reduce the time to simulate the circuit, and it will give accurate result. It will accurately match with your experiment result also. Okay, that is our experience. So we can construct any simulation within 2 days and any hardware within 1 week. That is our confidence with this. Okay. So I hope you will also get some confidence similar to us after this STTP or this wonderful program which is arranged by this sir coordinators. So with this, can we conclude this
All
session,
the
sir?
lab
Paras
session
sir?
will be taken by you, sir, na, sir?
What,
All
sir?
the lab session, all the lab session will be taken by you, na, sir?
Some other person will be there. The Junaid will take care of this, sir. If required, any session we will take. Okay.
National Infotech will take all the practical session.
All the practical session, yes, that will be taken by NITech, National Infotech, where Junaid will be there. He will guide you for this. Okay.
Okay,
Any
sir.
other query?
Any other query?
Sir, it is requested, please send the recorded video of this particular session, sir. It will be very
Yes,
helpful
sir,
for us.
that we will provide. Video link will be given to you. It will be put on YouTube, and you can watch those videos.
Yes, sir.
Okay.
Yes.
Thank you.
Any other query regarding today's practical session?
The practical way to simulate any circuit. This is the hands-on I have demonstrated with the 1 hour. Okay. So after that, you will see that same circuit. How can we program in the STM32 controller or STM32 controller? Okay. So I hope all are clear with this. Sir, we will conclude this session. Okay.
Yes. Thank you, Rajan, for such a wonderful session. We, on the behalf of SSBT College of Engineering, are very much thankful to National Infotech, and we expect for further participation in the same way for this STTP. Some instructions to participants. It is compulsory to register the link which is provided in the chat box, which is in the form of feedback and attendance. So kindly all participants go to the chat box and open the link which is being provided for the feedback and attendance. Second thing, the link for tomorrow's session will be sent in the evening itself today. So you can join tomorrow with that particular link. It will be mailed to you. Okay. So you may join that through that link. So thank you very much. I think we should conclude today's session, and I am very much thankful to all the participants for their patience hearing. Thank you very much.
Thank you, sir. So see you tomorrow.